Okay, this video should be for Secondary Math 3. It's notes on perimeters and areas of similar figures. All students will need the green packet, so please at this time, if you have not already, pass out the green packet to every student. And also all students will need a calculator. So if you need to pause, please pause and pass out the packet and make sure everyone has a calculator. Okay, so on your green packet we have, I just printed a PowerPoint, so it's divided up into slides. There's 4 slides on a page, and it's going to be kind of weird because most of the slides on the same page are almost identical, except for you're filling in an extra line. So if you notice, for instance, here, yellow is not a great color, here, here, here. As we go through, I'd like you to fill in the blanks, okay? So we'll just be adding some information on each slide. All right, so perimeters and areas of similar figures goes back to ratios and proportions. We know similarity, 2 things happen in similarity. We have, if you will recall, our purple pamphlet on similarity of triangles, for instance, which also applies to other figures, but similarity of triangles or other figures have congruent angles. That's important. But the sides are not necessarily congruent, but they are proportional. So they have a common ratio that holds true throughout the entire triangle or the entire figure. Just for make things easy, I'm going to start with 2 right triangles, because we know all right triangles are congruent. So here's a little right triangle, and here's another right triangle. As I said all right triangles are congruent, that's false. All right triangles are similar. Okay? And the base of the smaller right triangle is 3. The height is 4. If we use the Pythagorean theorem, 3 squared plus 4 squared equals c squared, we can find the length of the hypotenuse. 3 squared is 9, plus 16 equals c squared. 9 plus 16 is 25, equals c squared. Take the square root, and c equals 5. That's a very common right triangle, where the Pythagorean theorem works out nicely, which is why I chose it. Okay, so I'm going to erase this Pythagorean theorem work. We really don't need that, other than we know that the hypotenuse now is 5. Okay, the larger triangle, the base is 6. And we have what happens in similarity, something called a scale factor. Now, a scale factor says that corresponding parts are either growing or shrinking by the same rate. Okay, so if we move from 3 to 6, that's obviously growing, even though it doesn't technically look twice as long. Just pretend, use imagination. 3 times 2 gave us 6, right? So that's what our scale factor is. Our scale factor is 2. So all of the side lengths are going to increase by a multiple of 2. So they will be doubling. Now that doesn't mean the angles are doubling. The angles stay congruent. But the side lengths are doubling. Okay, so this side length was originally 4. Its corresponding side will double and become 8. Same with the hypotenuse. Was originally 5. Using the scale factor, we can say that that is 10. Okay, so on the slide, let's go to the first bullet point. If the similarity, that's not supposed to be ration, that's supposed to be ratio, just cross out that n. If the similarity ratio is A over B, then the ratio of the perimeter is A over B, and the ratio of the area is, now think area, what do we usually use with area? We say feet squared, we say inches squared, so the ratio of the area would be A squared over B squared. And the same thing happens with volume. If we went one step further and added in volume, volume is not squared, volume is cubed. So A cubed over B cubed. Perimeter is one-dimensional because you're just walking around the edge, just one direction at a time. One-dimensional, which is why we have just regular A over regular B. Okay, so let's see if this actually holds true. We said that the similarity ratio is A over B. So well, our similar ratio is 2, but that 2 is not a ratio. Let's make it a ratio. Do you agree that 2 over 1 is the same thing as 2? Yeah. Okay, so we have a similarity ratio of 2 over 1. Now let's look at perimeter. To help us visualize this, I'm going to actually, let's see, can I, oops, nope, can't do that. I was hoping I could just like copy all these and paste them into a second slide. Let's see if I can just select them. No, it's being picky. So I will just redraw them. Let's do that. I have an extra slide here. I'm just going to redraw them so we can just discuss what's really happening here. That's a little big. The first one's supposed to be small. 3, 4, 5. And the next one, I'll try to actually make it look double maybe, was everything doubled. So we had 6, 8, and 10. And we knew that our scale factor was the ratio 2 over 1. Now what's the perimeter? The perimeter of the first triangle is just walking the edges and adding them up, right? 3 plus 4 plus 5. 3 plus 4 plus 5 equals, well, let's see. 3 plus 4 is 7. What is 7 plus 5? You should have thought 12. Okay, now we're going to do the perimeters of the second triangle, which again, perimeter is just walking around the edges. So 6 plus 8 plus 10. 6 plus 8 plus 10. We can do this in our heads without calculators. Okay, what is 6 plus 8? You should be thinking 14 plus 10 is 24. Now, we said it's a ratio A over B for the perimeter. If we make this into the ratio 12 over 24, I did it reverse, okay, gives us 1 over 2, which, if we do the ratio, I'm sorry, I did this backwards, but if we had done the ratio of, we should have done the larger on top, the second triangle divided by the perimeter of the first triangle, we do actually get 2 over 1. And does that match our scale factor with the correct order? I did it in the wrong order. Yes, it does. 2 over 1. So that follows this right here, that the perimeter will give us a ratio, 2 over 1 in our case, because it was doubling. If it was tripling, it would be 3 over 1. Sometimes it could be even a fraction that's not an integer, 4 over 3. That would mean each side length is being increased by a multiplier of 1 1/3 if it was 4/3. Now, something different is going to happen with the areas. I chose right triangles for a reason, because with right triangles, we can easily find the area. Let me zoom out a little bit. It's a little large for me. Okay. Find the area of, let's start with the big triangle so we make sure we get it in the right order this time. Area of the second triangle. Remember, area is 1/2. Area is 1/2 base times height. Okay, so we're going to go 1/2. What's the base? We're starting with the second triangle. The base is right here. It is 6 times the height is 8. So 1/2 times 6 is the same thing as 6 divided by 2. 6 divided by 2 is 3 times by 84. 3 times 84. You should have, so that is 24. Okay, now the area of the first triangle. Well, the area of the first triangle, again, 1/2 base times height. 1/2 base times height. The base is 3 times the height is 4. That's why right triangles are nice, because bases and heights have to be perpendicular. And since we have this 90-degree square, we know that they are perpendicular. Okay, 1/2 times 3. Ooh, that's kind of weird. It's okay if you do multiplication out of order. 1/2 times 4 is the same thing as 4 divided by 2. 4 divided by 2 is 2. Times that by the 3, we get 6. So let's create these into a proportion. 24 divided by 6. Or I said proportion, I meant ratio. Ratio. 24 divided by 6 is 4. Is that the same thing as the perimeter? 2 over 1 equals 2? Are they the same? No, they're not. Because what happens with area, even though we're doubling the side lengths, area does not double. If area is being doubled, the side lengths are being doubled, the area actually quadruples. You take the scale factor and square it. So 2 squared would be 4, which means it's going to quadruple. So if you notice, the second triangle that has side lengths that are twice as long is now 4 times longer than the original area. We can go on. The volume would be the same. If we made it into, we'd have to make it into a prism. Both of them into, prisms, doubling everything. The volume, instead of being twice as big, we take the scale factor and raise it to the 3rd power. So the scale factor, again, and we were doubling, we're going to cube that. 2 to the 3rd power means 2 times 2, which is 4, times 2, which is 8. So 8 times larger. So let's recap what in the world all of this means. In 1 dimensions, when you double the side lengths of every side of the triangle, okay, the ratio of the perimeters is 2 over 1, which makes sense because all we were doing was doubling. But that's 1-dimensionally. Once you move to 2-dimensional, because we doubled the side lengths, 2-dimensionally, we don't just double the area, we quadruple the area. And if this was actually a 3-dimensional triangular prism, the volume of the larger triangular prism would not be doubled just because we doubled the side lengths. It would be 8 times larger. All right, back to the slides. Let's fill these in. So, zoom large. So this first slide really is going to be a key for you. So everything listed there is the key for the whole lesson. Okay, example 1. The trapezoids are similar. Keyword there, similar, means we can use the following relationships we just talked about. How perimeter will stay 1-dimensional. Areas relationships will be the scale factor squared. Volumes relationships would be the scale factor cubed. Okay, find the similarity ratio of, and you can read this better hopefully on your page than you can on my PowerPoint, of the top shape to the bottom shape. It actually tells you the order. Top first, bottom second. Okay, so let's look at the similarity ratio. On the next slide is where we'll fill in the answer. You can see I wrote in a blank. The similarity ratio of, again it said top first, divided by the bottom. Order is important with ratios. So that would be 9 over 6. Now careful, this does simplify. 9 divided by 6 is not 1/2. There's been this epidemic lately that everyone thinks fractions simplify to 1/2. It's not true. 9 I can divide by a common factor of 3, and 6 with a common factor of 3. 9 divided by 3 is 3. 6 divided by 3 is 2. So that is the similarity ratio. Okay, fill that in on your blank. Now it's okay that it's an improper fraction. Okay, the next slide. Oh look, it's already there. 3/2. We are right, good. We're going to find the perimeter ratio. Okay, the perimeter ratio, guess what? Is the same as the similarity ratio. Woo! Similarity ratio. So on the blank provided, fill in 3/2. It should match. Okay, flip your paper over. We'll find the area ratio. Let's see. Mine is right here. There we go. Okay, you can see on the back side of that page, there's a blank provided right here. So let's find the area ratio. Now be careful. Area is not the same. Remember, the similarity and the perpendicular are the same because they're both one-dimensional. But area, we're going to have to square. Remember, so we have a squared over b squared. So we're going to take that 3 and square it, divided by the 2 and square it. Okay, 3 squared becomes 9. 2 squared becomes 4. Now, do these two simplify? Do they have a common factor other than 1 that can divide into both? The answer is no. So 9/4 there is our answer for the area ratio. Notice it is different than the perimeter ratio because area is two-dimensional, so we square everything. All right, example 2. 2 similar polygons. So these are not triangles, not trapezoids, but we just have polygons. Have a corresponding sides in the ratio of 5 to 7. There are actually 3 different ways we can write ratios. 5 to 7 can be also written as a fraction 5 over 7, or with the words 5 to 7. Okay? 3 different ways you can see ratios. You should be comfortable with all 3 methods. Order is important. Notice the 5 always comes first, the 7 always comes second. So, and now, what is the ratio of the perimeters? Remember, perimeters and the similarity ratio are the same. Ding, ding, ding. They're the same. So if they tell you the similarity is 5 to 7, the perimeter ratio is 5 to 7. Easy peasy. Okay, let's go to the third slide, because each slide we just add one more piece. Oh, look. We're supposed to, that's where the blank is for that one. So fill in your 5 to 7 right there, because the blank was there. And on the bottom right square is where we actually add them in. Oh, look, the bottom right square, did they agree with us that it was 5, 7? I think they did. Okay, now you can see the blank is down here. Let's fill in what is the ratio of the areas. Okay, remember area. What dimension are we in with area? Are we in 1 dimensions, 2 dimensions, or 3 dimensions? Area is 2-dimensional. So we take our 1-dimensional information, 5 and 7, and we square them, which becomes 25 to 7 squared is 49. Now before you box this up, pretend it was a fraction. 25 over 49, would that simplify? Does 5 divide into 49? Because I know 5 divides into 25. 5 does not divide into 49. So that is your area ratio. If we had done the cube ratio, just for, this one's not really on your homework, but just for good information, we would have just cubed it. 5 cubed, 7 cubed. And these are going to be large numbers. So I'd appreciate it if everyone grabs your calculator. Grab it, please. Do 5 to the 3rd power and 7 to the 3rd power, please. I'll give you a second. Substitute, make sure everyone picks up a calculator, types in 5 to the 3rd power, 7 to the 3rd power. Okay, I hope everyone did it. 5 to the 3rd power is 125. 7 to the 3rd power is 343. This would be the volume ratio. Okay, and this is also, volume is assuming kind of that the depth of the 3-dimensional shape is 1, because we don't have the 3rd side, but pretend it's 1. Okay, next page. Example 3. The 2 regular pentagons are similar. There's that great word, similar. The area of the smaller pentagon is, 42.3 square centimeters. So I'm going to put that right here. Area equals 42.3 centimeters squared. What is the area of the larger pentagon? Area of the larger pentagon. So area equals x centimeters squared. Okay, well, we have information about the sides in one dimension. Okay, we have that this is 10 and this is 4, so let's make a ratio because that's our A over B. 10 over 4. And what does 10 over 4 simplify to? 5/2. Okay, go to the next box. Similarity ratio, we have it right here. 10 over 4 equals 5/2. That's the similarity ratio. Now we know that the area would be squared. 5 squared, 2 squared, if we had the perimeter. Okay, so let's come down here. Which one does it want us to fill in? Oh, you can see the area ratio is right there. So I just mentioned this. Area ratio, we take both of these and we square them, right? So 5 squared, 2 squared, which gives us 25 over 4. That is the area ratio. Let me do that in a different color. 25 over 4 is the area ratio. Now we're going to apply the area ratio in order to find the missing area. Does that make sense? We're trying to find the missing area, so we're going to apply the area ratio. Once again, it told us that this area was 42 point... Ooh, that's kind of not very pretty. Let's try that again. Area equals 42.3 centimeters squared. So we know 3 pieces. When you know 3 pieces, you can solve for the fourth using proportions. We know 10 centimeters, we know 4 centimeters, and we know the area. So we can solve for the missing area by setting up proportions. Okay, we have our area ratio is 25 over 4. Now here you have to be careful on matching things up. See the area we know? Does it belong to the larger or the smaller? Let's see, this is a pentagon. It belongs to the smaller one. So make sure, which one's smaller, 25 or 4? 4 is smaller. Make sure you line up 42.3 with the smaller value of 4. Here our area, x, we don't know, belongs to the larger. So we use x right here. Okay, we've talked about fishing method. I like fishing method, or you can just do inverse operations, cross product, they all work. So right here I see that we're dividing by 42.3. I just multiply by both sides by 42.3 to solve for x, to get x by itself. The 42.3's cancel out. So far today we haven't really done anything too difficult that you don't need a calculator for, but here's finally one where you do. Would everyone please type in 42.3 times, now when I type it in, there's a fraction. So I do parentheses, 25 divided by 4, close the parentheses. If you need a pause to let them all have a chance to type it in, please pause and ask everyone to type it in. Okay, I'll bring mine up now and type it in. Hopefully you've already done it. 42.3 times, I use parentheses around fractions always, 25 divided by 4, close the parentheses, and I get 264.375. Let's write that down. What was it again? I have it right here. 264.375. Now, what was this representing? This is representing area. So check out the units, centimeters. So we should say centimeters squared. That's the area of the larger pentagon. Okay, flip your paper over. I believe the blank is actually just asking for the answer. It says x equals, so recopy that. 264.375 centimeters squared. Okay, last problem. The area of two triangles are 75 square meters and 12 square meters. It asks us to find the similarity ratio and the perimeter ratio. Okay. I'm just going to draw some pictures so I have a visual. I'm going to tell us what type of triangles. I'm going to use right triangles just the 30. What is the similarity ratio? Okay, well, let's find first areas. Because remember, areas would be a squared over b squared. Okay, I'm going to put the big one on top, that way it has the potential to divide nicely. So I'm going to do 75 divided by 12. And you know what, I think that simplifies, doesn't it? 75, I know 3/4 make 75 cents. Do you agree? 3/4 makes 75 cents. So I'm going to divide by 3, and I get 25. I also know 12 divides by 3, which equals 4. Does 25 simplify further with 4? No, it doesn't. Okay, so this is the simplified form of the area ratio, but that's not what we're asked for. We're asked for a similarity ratio. And remember, similarity ratio is one-dimensional. So we don't want this squared. How do we get rid of a square? Take the square root, right? Because all we want is a divided by b, just regular a divided by regular b, not a squared and b squared. So what we need to do is take the square root of 25 and the square root of 4. The square root of 25 is 5, the square root of 4 is 2. So that is our similarity ratio. It's 5 over 2, which guess what? Also happens to be the perimeter ratio. Okay, that's the end of the notes. For the rest of class, you will be working on your assignment, your book. The book assignment is page 572, 2 through 40, even. There are 3 steps to do your homework correctly. Number 1, write down the problem, which for many of these means copying down the figures and labeling the shapes. 2, show your work. 3, box up the correct answer. Please make sure you're doing all 3 steps. Remember at to area, let's go back to and just review that very first slide. Right here, I think. Yes. The slide I highlighted in yellow. Remember, similarity ratio is A over B. Oops, get my color. Guess what? Perimeter ratio is also A over B, so they are the same. Yay, easy, they are the same. Ratio of the area is area, remember that is squared. A squared divided by B squared. And you don't have volume on your homework, but it's good information. It is A cubed divided by B cubed. So on your homework, you only have the area, well, similarity and perimeter, which are equal, and the area. Okay, remember area is squared. If you're reversing backwards, you're given the area and you have to find the perimeter or the similarity ratio. As the last example we just did, you remember to take the square root. And then you're good to go.